welcome to signal processing for millimeter wave communication for 5G and beyond. So, today we will be covering the MIMO FDM part. So, last class we have covered the single input single output FDM structure, and also we have explained little bit about the CFO part. So, today we will be graduating to the MIMO and then we will be entering into the MIMO beamforming, MIMO FDM beamforming. So, that is the final goal of this particular module. Okay, so let us see that what we will be covering here. So, we will be just covering a very simple thing that is called a MIMO FDM structure. So, let us now go back to our structure again. So, we have already known what exactly FDM is. So, now let us get into the MIMO part here. So, let us assume that for a single antenna case, this was the structure, right. So, you have a FIR filter which was H0 plus dot 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 . Okay, so, that was the filter, and finally, we have known how exactly an FDM things work with CP addition, CP deletion at the receiver, and how the whole channel becomes circular channels, and what are the advantages and what is the effect of CFO. We have also discussed it, and what are the different spectrum moment you do FFT, IFFT, moment you do an IFFT, what is the time domain spectrum of it, everything we have discussed. So, in a very simple sense, you can think of FDM as a filter bank. Okay. So, another view of FDM is that it is basically a filter bank. FDM is nothing but a filter bank. Filter bank at the transmitter, naturally there will be a counter filter bank at the receiver, and that is nothing but the IFFT. So, if you have the IFFT matrix, so this is your IFFT matrix. So, this will be 1 1, then it will be 1 omega, of course, omega square, then omega star cube. This is IFFT matrix. This will be omega, omega star or omega star square, you can say that way, then omega star 4 and so on and so forth. So, you can think of this whole thing as a filter bank. What is filter bank? It means that series parallelly there will be a lot of filters and the data is going through each other. So, the data is your S vector. Okay. So, you can think of, so this is one filter bank, this is the second filter bank, it is an FIR filter you can think of, whose coefficients are the following. The third filter bank, and there will be n number of such filter banks. So, each and individual one is a FIR filter whose coefficients are so and so, you can think of it that way. So, which means that your FDM is nothing but, so you have a data which is your S vector. So, there is a first filter, there is a second filter, and there are nth filter, nth FIR filter, and each and every filter has a length n. This also has a length n, this also has a length n. So, the data goes everywhere, and that is precisely why multiplication also shows the same thing. So, here it shows precisely the same thing. So, this is the first filter, first one, and there is a second filter whose coefficients are written as I have written here, and third filter and so on. So, these are the coefficient you can think of. Okay. So, like that it will be n filter, and finally, what you do, you just merge them all together. So, this one will be having a spectrum like this, probably here. This one will be having a spectrum like slightly shifted, not shifted like that here. Third one will be having whatever, it is like a shifted. The third one will be having a spectrum like this, fourth one will be having a spectrum like this, and so on and so forth. Like that, there will be n number of such spectrum, and we have explained that all the spectrums are overlapped. So, there is a counter filter bank at the receiver, they are nothing but the FFT filter, and what the FFT filter will do, they are basically, that filter is nothing but a sampler. Okay. So, what it will do? It will sample the spectrum at a particular point, and the output spectrum is a discretized filter, discretized spectrum. So, okay. So, we have explained all these things, and we have also explained what is the effect of CFO. Now, we are graduating to the MIMO part. So, what happens when I go for the MIMO? Now, when you go for the MIMO, so let us take a very simple case. Let us say I have two antenna here. Now, all these things will be required when you go for the beamforming aspect. Okay. So, there will be MIMO waveframe beamforming. So, let us say I have just taken a very simplistic case where you have a two antenna and two antenna at the input, two antenna at the output. So, this is my TX side and that is my RX side. Okay. Now, what is the big deal about it? I would say it is just an extension. So, if you understand how the first one works, this will be just a cakewalk. So, you can think of, so this is the first antenna, this is my second antenna, this is my first antenna at the receiver, this is my second antenna at the receiver. So, you can generalize. So, how you can perceive this channel model, because when you say WaveDM, then naturally I would not consider channel to be a single tap channel, okay? Because if it is a single tap channel, there is no point of going for WaveDM. I mean, you can anyway you do not have any ISI. So, WaveDM will not do anything extra. There may be spectral efficiency, but that is except that I mean there is no ISI removal for that, because there is a single tap channel, there is no ISI anyway. So, but here the actual benefit of WaveDM is basically coming from the fact that it has an ISI and you are not removing the ISI, but doing some internal processing like IFFT and FFT. You are squeezing you are removing the ISI, not removing, I should not say the removing the ISI, I would say that you are making the channels or the system as if like the whole system is like a ISI free system, as if like that. Okay, that is the advantage. So, the channels I have to consider them as a FIR filter. So, that means when I say I am taking an MIMO, it is just that I am taking each and individual link channel antenna to antenna link all in the digital domain. See, antenna to antenna link as a FIR filter. So, this will be my FIR filter number, I call it H1. It is an FIR filter. So, which means that it will have L number of taps or whatever. Similarly, I will have this, maybe I call it H12. Now, this H11 it is all Z transformation, I can say, because it may have multiple taps, just the way we express a filter, right. And this probably H21, this is the channel, and finally, this will be another channel. Z is there, not to worry about that. So, each and individual, so I can say H I J Z will have, it will have n number of taps. Now, does it assume that each and every link from antenna to antenna is having equal number of taps? No, there is no such things. I can have any number of taps. There is no such risk. In fact, if you understand, the WaveDM really does not care about that. How many these taps are there, frequency domain taps are there, really, it really does not matter. Though I have not discussed the channel estimation part really in this context of WaveDM. If the time permits, probably at the end when we go for the parameter estimation in the context of beamforming, I will definitely touch upon that, how exactly channel estimation for the WaveDM system is done. So, there you will see that I really do not care about H0, HL1. So, what matters is the eigenvalues, because at the end of the day is the eigenvalues that gives me everything, right. So, it really does not matter. So, it really does not matter what exactly the length of this channel, what matters is the eigenvalues. Anyway, so let us assume that this is what my complete system, and I would like to have the WaveDM system here. So, what exactly I need to do here is that, so this is my first individual transmit antennas. I am making it equal antennas as the transmitter and receiver, but nothing stops you from generalizing it. So, you can have NT number of antenna here, you can have NR number of antenna here, but these are not beamforming antenna, mind it, they are just data antennas. I have not introduced the beamforming. Okay. So, this is just the data antenna. So, what I will do here, you can let us take a 2 for simplicity, then in the same equation I can generalize it to. So, let us say, so the way the structure would be, each an individual transmit antenna will be, you can think of it like a one waveform system. So, what you do here, I can say this is my S vector which I was transmitting it earlier. Now, instead of S vector I call it S1 vector, because that is it is a n length, total n length vector. So, this will be n cross 1 length vector. This individually I will send it through an IFFT, then there is a CP addition, and then I will send it to the antenna. Okay. So, that is the part. So, it is like a every antenna is self sufficient from an waveform structure point of view. So, it is as if like you do not consider the Rx part, just consider the Tx part. Every antenna will be feeding their own individual data, n length data. So, each and every transmit antenna is like a one waveform link. So, here similarly I will have S2 vector which is also an n cross 1 vector. I will have IFFT, then I will have CP here, I will feed this. Okay. See, if I have if you generalize it, obviously that many number of structures. So, that is the only change in the transmitter side. Okay. So, this is the extra part. So, now every antenna, so if you notice how a non waveform MIMO works is that at a time every antenna will be delivering one individual data. So, here also it is happening the same way, but now there is a catch. The catch here is that earlier case when you just consider the MIMO, plain MIMO, it was more on the spatial domain, meaning you are at a particular time your channel is structured, but now that is not the case, because every antenna is getting a serial data of n plus k length data. Okay. Now, another point that I would like to make it clear, the CP length has to be same. Okay. The individual channel length can be different, somebody have L1 channel length, L2 channel length, L3 and L4 does not matter, but the CP length has to be same. So, which means that if the CP length is k, this k must be greater or equal to your max of channel length. Suppose there are, in this particular diagram there are 4 channel blocks are there, right, 4 channel FIR filters are there, and assume that everybody has their own channel length, tap length. Okay. So, whoever is the max, I need to pick up k max of all of them. So, k is uniform. If the k is not uniform, then whole things will collapse. Okay. As I said, I really do not care about the channel length. So, I will always pick up a number which I would feel that okay, my channel lengths are all within that. So, as long as that part is ensured, the things will work. Okay. So, this is how the transmitter side is. Now, let us go to the receiver side, what happens. Okay. So, let us go back here. So, here just think of the first antenna, okay. Just think of the first antenna. So, the first antenna receives the data from the first received antenna takes the data from first transmit antenna and the second transmit antenna, right. Okay. So, you can say that this Rx 1, the first antenna of the Rx, if it takes n plus k length data, so what will happen if it is an n plus k length data. So, I call it say y1 bar. So, if it is say n plus k cross 1. So, what will happen? It is the data which is coming from the first, which is due to the first antenna. So, there is an n plus k cross 1 and there is a what is y11? Y11 is basically received data from the first antenna. Y12 is the received data from the second antenna. So, it is when you say y11, you just think that the second antenna, second transmit antenna is not present. It is like the H, it is solely responsible by the H11 kind of things. Okay. So, that is the only thing. Now, you can imagine what can happen. It is just that it is instead of one WebDAM received data, I will have two WebDAM received data, that is all, rest is same. Again what you do, you discard k, the first k, not the last k. So, if you have y, one, let us say this is my k and this is my n, this is the total n plus k data, you discard this part, just the way we have done it in the WebDAM also, you take the last n data. So, what will happen? Then I will get one, what is the effective data then? So, it is as if like, it is as if it is to summation, right. So, the first summation and there is a second summation. The first summation is an individual WebDAM, second summation is another individual WebDAM. So, that is all. So, if I discard it, so let us call it H11 C, it will be circular channel, right, and it is completely S1 vector. This is precisely what we have done for the single antenna, single antenna and single received antenna case. This will be, what was the antenna? This will be H21. So, this will be H21. Now, I put C because just to ensure that it is a circular channel, because it will be circular channel once I discard the N. So, this will be your S2 bar. Okay. Now, what do you call it? So, this will be Y11 or rather Z11, let us call it just for simplicity Z1, which is a n cross 1 length data. Now, this is precisely the case. So, this is my equation, say let us say 1. Now, in the earlier case, if it was a pure single antenna case WebDAM, this part was not there, that is the only thing. Otherwise, it is just another terms will be added. Okay. Similarly, for this is my case number 1. Similarly, for a second antenna, second receive antenna, this one. Okay. What will happen? So, let us call it Z2 n cross 1, right. So, this will be, let us see what else comes. For the second antenna, it will be H12 and H22. So, this will be H12, but it is the S1 data, right. This will be H22. This is my equation number 2. So, this is the pre FFT data, I received it, that is it, I am done. So, now these are the two data that I have received it, okay, after the CP discussion. So, in this diagram, when I go for the receiver, what I need to do? I received individual data at every receive antenna and then I discard the CP. So, which means that in this diagram, let us remove this part. Okay. So, this is my antenna number 1, this is my antenna number 2. So, the first thing I do here at individual is I discard the CP. Here also I discard the CP. What I received? Z1 vector, here I received Z2 vector. Then what I do? I do the FFT. I do effective operation. Here also I do effective operation. So, I multiply it with the F matrix. I should naturally guess R1 vector here, R2 vector. Now, let us see what is exactly R1 and R2 vector. So, that is the point. So, I have just done CP discard. Then what I am proposing is that now, as the structure suggests that everything is a circular channel matrix, I should just do an FFT. So, now you do an FFT, that means every Z1, every Z2 will now go through an individual FFT. So, what will happen? So, let us call it R1 vector, which will be F into Z1 vector. So, now it will be F, H11 is there. Okay. So, let us break it F star sigma 11, let us call it, okay, F, okay, and here, yeah. So, just a second, I call it X, let me call it X, so that it will not create any confusion. This is what a transmitted vector. What is x 1 and x 2? So, basically this one is your x 1 vector, this one is your x 2 vector. So, that makes the life slightly easier. So, this will be f star into s 1 vector plus f star, let us call it sigma 2 1. So, let us call it sigma 2 1 f star s 2 vector. Okay. So, make sure that it is x 1, x 1 is the one which is transmitted, this is the IFFT data, it is not S 1. So, what it would be? This will be gone, this will be gone, this will be gone, this will be gone, right. So, it will have a sigma 1 1 S 1 vector plus sigma 2 1 S 2 vector, that is the only thing. So, let us call it equation number 3. Okay. Now, you see that it is a summation of two individual two individual summations. Okay. Number of, now, if I generalize it, so from here itself I can generalize the transmit sectors. Let us say I have an NT number of transmit. So, what can I write? This equation number 3. Can I write it like that? Summation of sigma say L, okay, 1 S of L. Let us say L is equal to 1 to NT. Do you agree with this? Let us say this is 3.1. Just a generalization. Suppose I have, instead of 2 transmit antenna, I have NT number of antenna, transmit antenna. So, I will have NT number of such sigma, right. So, that is precisely what I have done. You have NT number of such sigma, and then you have NT number of such data vectors also present, right. So, that is the generalization, that is okay. Now, similarly, I will have R 2 also, right, in the case R 2 also. Let us take second case as well. Now, this is a special case, I would say this is a general case, 3 is the special case of a general. So, I just put it in a bracket, and for the R 2 vector I just make an extension H 1 to H 2 2. So, what will happen? Sigma H 1 to S 1 vector plus sigma 2 to S 2 vector. Okay. Now, this is precisely what happens when you go for a data. So, let us call it equation number 4. Can I generalize it? Of course, you know how to generalize it. Now, can I generalize the R vector also? Of course, because this is only for R 1 and R 2. If I assume there are only 2 received data, can I generalize it from the receive antenna point of view? Yes, you can. So, that means even more generalization at the receiver side also. Listen, at T x R x both. So, what is that? Simply I am assuming now there are NR number of received data. So, you have NR number of received data, NR indexed total data. So, let us call it even general one. So, let us call it say R m, and mth, the mth received data, where m starting from NR, any one of them. So, how do I generalize it? It will be summation as usual 1 to NT, is the case, then sigma. So, what was the case here? L 1 here. So, this will be L and this will be M, okay, and then S L, that is all. That is the generalized data model. So, if I say that is my generalized data model. Generalized received data model at the mth received antenna, but that is okay, you can think of whatever way you can have. So, now I am not putting any restriction on that. Now, let us get into the, so this is the main part of my OFDM MIMO OFDM structure. So, as long as you get your data, so that means at each and individual received antenna. So, at the end of all this operation, what R 1 or R 2 gives me is a summation of multiple OFDM structures, that is all. After the removal of your CP and after doing FFT, that is the data that I will receive it here. Okay. So, this is the main part of the this is the main part of the WebDIM structural point of view, but what I have not yet done is that how do I decode it? Can I decode R1 and R2 individually? Let us discuss that part. Okay. So, I got the data, that is fine. So, let us take a simple case, our simple data model. Okay. Instead of generalized model, let us take the this particular model, first one. So, equation number 3. Let us take the equation number 3 and equation number 4. Okay. So, this one, just 2 antenna case. Now, every individual data, every individual received antenna, they have got their data model after FFT. Can I decode individually? That is the point. Notice that equation 3 and 4, both of them contain S1, he also contains S1, he also contains S2, he also contains S2, right. So, if that is the case, how do I individually decode R1 and R2? So, that was the case for single wave antenna WebDIM case, CISO WebDIM case. There you just receive a data, then what will happen? You take the vector, take the individual point, I mean the say ith element of R vector, and I can decode it like a normal AWG antenna, but this is not the case. If you take the ith, let us take the ith, say R1 vectors ith data, what it will contain? It will contain some. So, this was say sigma 1 1. So, it is the ith diagonal element of sigma 1 1. Okay. So, let us call that E 1 1 I. Okay. It is the ith diagonal element of E 1, that is the eigenvalue of that matrix, plus what? Plus S 1 vectors ith element, plus what? What else is there? S 2 1, sigma 2 1, E 2 1. So, E is what? E is a vector containing all the diagonal element of sigma. So, basically what I am trying to say, E 1 1 is nothing but this sigma 1 1, that is the matrix, right, but it is a diagonal matrix. So, the all diagonal component. So, if I write it, put it this way, probably I put a different notation, it is the diagonal element of all this sigma 1 1 matrix. So, that is E I, E 1 1 vector, it is a vector, right, E 1 1, this is a vector, I should write it is a vector that contains all the diagonal element of that matrix sigma 1 1, let us assume that, it will be easier to understand. So, here also similar notation, but now this is I. I have not used the noise here, you can use noise, that is not a big deal. So, here also you should have a noise vector. I mean, I have not conveniently used this noise part, because that is not our goal to, I am not doing an analysis, but let us okay. You can have a noise vector just for your completeness, I do not mind it. Okay. So, you can have a noise everywhere, you can have noise, yeah, you can have noise, yeah. So, that is not our. So, just for your understanding, I just put the noise here, yeah. So, this is the case now, that means at my receive antenna, the ith element is having this part and this part. So, now there is an ISI again. Now, this ISI is not exactly, I should not say it is an ISI rather, because ISI enters symbol, but it is not from the same antenna, but from a different antenna, okay. And at the same time. So, this is an interference for R 1 1, or if I take S 2 as my data, then S 1 as my interference, or if you say no, there is no interference, because both of them are important to me, then it is as if I am again coming back to the same scenario earlier, that when I was dealing with the ISI channel, that I have one observation from where I have to determine two unknowns. Okay. So, now this whole MIMO FDM will stop me from doing an individual decoding that I did it for the FDM, because now I cannot take the ith element of my vector and decode for S1 and S2 and so on and so forth. Similarly, if you go to R2, I am just motivating you, R2, this will be a similar situation. Similar situation, that when I take the R2, this also has the same problem, both of them are 2. So, I cannot take individual point and go for a decoding. Okay? This is not possible. I should put a different color of line, because both of them. But have you noticed one thing here? Probably that is the motivation for my next class. Motivation is that if I observe both of them together, instead of taking one individual, let us take them as together. That means, I am stacking them together. That means, both the equation if I consider it together, as both of them have the same variables of interest. Now, I am in a better position. Now, I have two observation, but two unknowns. Can I decode it? So, here if I take them together, instead of thinking ith element of individual data, I take ith element of all of them and stack them together. Okay. So, two observation here I would say, and here two unknown. Now, I am in better position. So, if I take both of them together, I can decode this fellow properly. Instead of individually, if I take them, why is it happening? Because both the equation have variable of interest same, both of them have the same variable of interest. So, why do not you merge both of them together, rather why do not you consider them as a vector, the observation vector, and let us see if I consider whole thing together as a vector, what will be the magic that is coming into picture. Okay. So, that is where the extra part that MIMO FDM will offer, that is extra part, and we will see in the next class how we solve this equation from a linear algebra point of view. Okay. So, with this I conclude the session, and in the next class I will be talking the decoding part of the MIMO FDM. Okay. So, with this I go back here. So, conclusion is that we just covered the structure of the MIMO FDM, how the structurally it can be presented. I think that should be made it clear. References are again these are all a very standard part. I do not find any one point references, but IEEE Explorer, if you go and type MIMO FDM, thousands of good references will be there. But so, I put IEEE Explorer as one of the rich source of contents instead of just saying one content. Thank you.